Hopefully some of the pieces are starting to fall into place in our study of electrostatics. No doubt you've seen the similarity between Coulomb's law and Newton's law of universal gravitation. Coulomb's law is an inverse squared law. The force between any two charged particles 1 over 4 pi epsilon naught q1 q2 over r squared. Let's make this a vector equation. Newton's law of universal gravitation, force of gravity, is equal to a universal gravitational constant times the mass of one object times the mass of another divided by the distance between the two squared. Sometimes we just refer to this as K equal to approximately 9 times 10 to the 9th Newton meter squared per Coulomb squared. And as you recall, the universal gravitational constant is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And I write out these constants just to remind you that this is a very small number. And so unless one or the other of these two masses is really large, there's not going to be an appreciably large force of gravity. However, in the case of electrostatics, this is a very large constant. And even when these charges are small, you still have a large electrostatic force. This epsilon naught is known as the permittivity of free space, and it's equal to 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. Okay, so both inverse squared laws, fine. You've also seen probably the similarity between these equations. We can find the net force on an object if we multiply that object's charge times the net value of the electric field wherever that charge is located. In the same way, we can find the net gravitational force on any massive object if we multiply times the net gravitational field. Now, if it's just a single charge, right, if there's just one monopole creating the electric field, well, maybe we'll call that charge capital Q, and we place this other charge, lowercase q, then we don't really have to say there's a net electric field. We can just say F equals QE. So in that case, the value of the electric field at this point, if we rearrange this equation, is F over Q. And so if we use Coulomb's law and just consider magnitude, this is K times capital Q times lowercase q divided by r squared, and then I'm going to divide all that by the lowercase q, by the charge I'm placing here. And so the electric field produced by any monopole is just Coulomb's constant times the amount of charge creating that electric field divided by distance squared. Now, what distance are we squaring? Well, it depends on what location you want to know the strength of the field. If I want to know how strong the field is here, then R will be this value. If I want to know how strong the field is at a point a little bit farther away, then it'll be a larger value of R that I would use in that equation. So at every point in space, there's a unique value of the electric field, and as long as I know how far away that point is located, I can find the value of the electric field at that point. And in the same way, if we just have a single celestial object, whether that's a star, a planet, or a moon, let's say this is some planet, whether I place a satellite in the vicinity of this planet or not, at every point there's some unique value of gravitational field strength. Now, as soon as I do place some massive object, let's say at this point, then I can find the amount of force, so I don't have to talk about net gravitational field. There's only one gravitational field here being created by this planet, so F is equal to mg. G is F over m, and as we know, we can find the gravitational field around at any point around a planet as long as we multiply the gravitational constant times the mass of that planet and then divide by the distance we're interested in squared. So these similarities hold up not only in the equations for comparing force, but also in the equations for calculating field strength. So it really comes down to whether or not we have individual points of charge creating the electric field, or we have uniform field. In other words, I can give you a problem like this. So there's one charge, Q number 1, located along the y-axis. There's a second charge, Q number 2, located on the negative y-axis, and a third charge, Q3. And we can make up some values here. Q1 we'll say is equal to 5 nanocoulombs. Q2 is equal to 3 nanocoulombs, and Q3 is equal to -2 nanocoulombs. And we can come up with some values here. Maybe this is 15 centimeters, and this is also 15 centimeters. This is maybe 25 centimeters. And the question is, what is the net force experienced by this charge Q3? So I can use the superposition principle. I can take the equation that says the electric field created by any one charge is equal to K times that charge divided by distance squared. Now, using a little bit of trigonometry, I can figure out what is the distance between Q number 1 and this point in question. So I'm going to say the location of charge number 3 is just at some point P. And that way, whether this charge number 3 is there or not, there's still some overall net electric field at that point that has nothing to do with the value of the charge that I place there and only has to do with the value of the other charges, right? So we can have electric field number 1 due to this charge number 1, and there's also, which by the way would be a vector. Electric field's a vector quantity, and since this is a positive charge, electric field vector number 1 points in that direction. Now our second charge is also positive but smaller in magnitude, so there's going to be another electric field vector pointing this way, but I draw that vector shorter, right? Because this force is definitely going to be smaller in magnitude. It's the same distance but a smaller amount of charge. So electric field vector number 2 would be equal to K times charge number 2 divided by r squared. I guess I should be consistent. If I use lowercase q in each of these cases, I'll use lowercase q here. All right. Now, if I want to find the net electric field at point P, I'm not going to just take these values and strictly add them together as scalars. I'm going to have to do the vector math to figure it out. And that's really not the point of this video lesson, is to do the numerical computation. It's more to express the method by which we would do this. So if you feel like you would like to do it and use the values given, by all means, you can work this out. In the end, we set up the problem by saying a charge of -2 nanocoulombs will be placed here. So whatever we end up with as the net amount of field, the force on that -2 nanocoulomb charge would be equal to 2 nanocoulombs multiplied by whatever the value of the net electric field is. Now, I could put in negative. That's not going to change the magnitude of this answer. The negative is just going to tell us in what direction. And by the way, a vector summation of vectors that point roughly like this, we can use the parallelogram method. So the net electric field is going to point basically in this direction. So had we put +2 nanocoulombs here, then it would accelerate this way. Because we're putting -2, we know it's going to accelerate this way. So that's all we know about the negative sign, right? It doesn't change the magnitude of the force or acceleration. All right. Then again, we might encounter problems that aren't so much due to discrete particles, 1, 2, 3 charges. We might have something like a continuous distribution of charge, right? Instead of little points of charge, we've spread out positive charge as a distribution across this top plate, and we've spread out negative charge and distributed all across this bottom plate. And as you know from our previous lesson, that produces a uniform electric field in the interior space of this parallel plate capacitor. And so there's no need to use equations like F equals K Q1 Q2 over R squared, or E equals K Q over R squared, because we don't have discrete particles. In this case, E is not calculated in any formula. It would probably have to be given in a problem like this, right? It would just be represented as some singular numerical value. Maybe the electric field is 2,000 newtons per coulomb. Maybe the electric field is 150 newtons per coulomb, whatever it is. It's just some numerical value expressed in newtons per coulomb. And so if the electric field is just a constant, then the only equation we need is the one that says F is equal to QE. Same thing when it came to gravity, right? If we had Jupiter and the Earth and Mars, and at some moment in time they're all aligned like this, right? They're all orbiting in nearly circular paths. The sun is somewhere over here. And there's a spacecraft right at this point P. We have to find the net gravitational force acting on that satellite. Well, we're going to have to know the mass of the satellite, but we can take it one step at a time using the superposition principle and say that the gravitational field is equal to G times any one of these masses. I can start with Jupiter. I can take the mass of Jupiter and then divide by the distance from the satellite to the center of Jupiter squared. And then I'll do that same process again. I'll find the distance from the satellite to Mars. And then this is no longer the mass of Jupiter. This is the mass of Mars. Anyway, I'll end up with 3 gravitational field vectors that I have to add using the methods of vector mathematics. And I can find what the net gravitational field is at that point. So in the end, the net force acting on the satellite will be the satellite's mass times that net gravitational field. But we certainly wouldn't do that to figure out what's the force on an object that's released from rest in this classroom, for example. Okay, so the gravitational field is just uniform inside of a classroom. If we take a mass of m, there's no need to invoke the equation F equals G m1 m2 over r squared, or that gravitational field is G times m over r squared. No point in that. G is just a single constant numerical value, 9.8 newtons per kilogram. So the only equation we need is F equals mg. So how do we know when to use these equations? We have, let's list them all, right? We have electrostatics equations, and I think it's helpful to compare them to equations we're already familiar with from our study of gravity. So there's an equation for force known as Coulomb's law, and here I'll just state it as a magnitude equation, not a vector equation. F equals K Q1 Q2 over R squared. We also have an equation that says any single charge creates an electric field. E is equal to K Q over R squared. And then we have the much simpler equation, just F is equal to QE. Okay, so likewise in our study of gravity, F equals G m1 m2 over R squared. We can find the gravitational field around any single body as G times the mass of that body divided by R squared. And of course, once I know the overall gravitational field at some point, I can find the force on any additional mass by multiplying it times the strength of the gravitational field where it's located. So how do I know when to use each of these equations? Well, it's all taken in context. But generally, if you can see some sort of diagram, maybe you'll encounter a problem where you're told that 3 charges are located at the vertices of an isosceles triangle. What's the amount of force on this charge? Certainly, we're going to want to use an equation like this. So this would be referred to as a problem in discrete charged objects. Right? Discrete just meaning separate, individual. If you can point them out, oh yeah, there's 1, 2, 3. In the latter half of this unit of study, we're going to investigate how much force there would be if I had a charge, let's say, maybe there's a plastic rod and I've rubbed it with rabbit's fur, and so I've spread out charge uniformly across here. Well, we need to come up with some equations that tell us how strong would the electric field be at this point. Well, I can't use the equation E equals KQ over R squared because this rod is not a point charge, right? So I can divide it into little chunks and say that's some amount of charge, dq a little bit of the overall charge, capital Q, and then the distance between this point P in question and this bit of the charge can be found using this equation. But then I'm going to have to divide it up. Here's another little chunk I have to account for, a separate dq. And the distance here is a little bit greater, so that changes the value of R. And so there's a little contribution to the electric field, dE, due to this charge, and another contribution to the electric field, dE, due to this charge. And in the end, I'd have to sum all of that up. So we're going to have to use some calculus to come up with other equations for finding electric field that differ than the form given by Coulomb's law. In the end, whatever equation we use to determine the electric field, whether it's the electric field around a charged rod or the electric field, here's another problem we'll end up solving before this unit's over. What if you had a ring of charge and you distributed electrons uniformly around it? Trying to make this a three-dimensional drawing, so we've got the y-axis, the x-axis, and the z-axis, so we're viewing a ring sort of on edge, and we have to figure out what's the electric field at this point. Or maybe it's not a ring of charge, maybe this is a solid disk that's charged up, and we want to know what's the electric field strength at some point down this axis. Well, it's not exactly a uniform electric field. As long as we stay to regions close to it, it is, but as we get farther afield, these field lines start to curve, and so this remains a question. In any case, as long as I know the expression that tells me how strong the field is, then if I want to find force, I'll tell you I'm going to place a charge Q at this point. That force is going to be Q times E. So we have distributions of charge like charged disks and charged rings and charged rods. In all those cases, we'll end up using this formula, which seems easy, but we're going to have to use calculus to figure out this part first, okay? And then we have discrete charges. Whether it's three charges on the vertices of an isosceles triangle, or we just have two charges that are along the x-axis and we choose to place a third charge somewhere on there. Maybe we have charges 1, 2, 3, 4, and the corners of a rectangle, whatever the case. If we can count them out as individual point charges, then we can use the formula E equals K Q over R squared. By the superposition principle, we can find the net electric field, and once we have that value, the net force is Q times the net electric field. So, distributions of charge versus discrete charges. It's up to you to determine what equations to use in the context of the way in which the systems of charge are distributed.